Well, we're happy to have Rod Brown, our Secretary-Treasurer, give this talk. His first talk about telescopes was in May, and this is the second installment. So, as you know, Rod is not only Secretary-Treasurer, but also wears many hats. You heard about his expertise in telescopes, and he is also an organizational wizard. We can talk about that infinitum. But anyway, let's welcome Rod.
All right, thanks everybody for coming out. And as Greg mentioned, this is going to be part 2 of what I started talking about back in May. Back in May, I call it the Quick Start Guide. It was the goal was to get you out there quickly and looking at the night sky. So now we're going to step down one level of detail. So we're going to talk really about equipment for a bit. Then we'll relate that to coordinate systems. So you saw the grid on those maps that Greg had up during his presentation, and we'll talk about what that means and help answer Bob's question too, or explain Bob's question. One thing I want to point out here too is that the focus tonight is going to be on visual observing. Everything is very general. It relates to doing astrophotography as well, but astrophotography is a whole nother huge separate discipline, and we're not going to go into those details tonight. We've had some presentations. Look to our YouTube channel for those. And I also should mention smart telescopes. This stuff applies to them too. You heard Mark talk about that a few months ago as well. They simplify some of this, but again, we're not going to get into those details either. So first, let's start with the real big basics. Why do we need telescopes? So really, as you might expect, we need them because things are far away and they're very small. If you look here, these are relative dimensions of the moon, the big sphere that you see there. And you can see up here, Jupiter. Jupiter, when you look at it, is relatively the size of one of the moon's craters, so it's pretty small. And Jupiter is the biggest of the planets when you look at the sky. Everything else is smaller. So the arcs that you see on either side are that diameter of the full moon, and you can see relatively how everything is much tinier compared to that. So we need to make things bigger. The other key thing is that objects are faint. I think we all know that, but the key part is that our eyes are, relatively speaking, compared to a pair of binoculars, pretty small, and even smaller if you compare them to what's just a small telescope. Obviously, things aren't that big in real life. Your eye's not that big, but think of these as all relative to each other. And when we increase that diameter and increase that aperture, we'll talk about the term aperture here in a little bit, we're able to get more light and see fainter things. Okay, with that as the background on why we have telescopes, now let's talk about types of telescopes. So really there's 2 main types, and then there's one that's a combination of the others. So refractors, so this is a refractor, a very simple one. You got light goes into the front, there are lenses up here, and it comes out the back through an eyepiece, and we'll talk about eyepieces, but it's the lenses up here that do that magnification in combination with the eyepiece. The other type of telescope is a reflector. So I know this doesn't look like it, but this is a reflector telescope. If you look down inside, you will see a mirror down in the base of it. And so the light comes in here in the front, hits that mirror, goes up and is reflected by a flat mirror out through the eyepiece. And it's that curved mirror in the back that does the magnification in this telescope. We also have catadioptric telescopes. These are combination telescopes. They have essentially multiple stages, a combination of lenses and mirrors that do the magnification. So here's a sort of a cutaway view of that telescope. You got as I showed it, that the light's entering the front. There is a mirror, and the example here, that one didn't have one, but a lot of times you'll see a mirror that basically moves the light at an angle, but it's flat, so it's not doing any magnification. So sometimes you'll see a mirror that does no magnification as well. So talking a bit more about refractors, there's some challenges with them. One of those is that lenses reflect different wavelengths of light, different amounts. And that's one of the challenges with the telescope, is that you need to get all of those different wavelengths to line up. Otherwise, your image looks blurry with the different colors at different positions like you see there. So telescopes use a combination of different elements of glass and coatings to get all that to line up well. Refractors can be small or big. The one in the upper left there is basically 1.5 inches. That is what Galileo used to do his first observing. They can also be giant. That one you see there on the right is in Wisconsin. It's actually 40 inches in diameter. And the one down at the bottom, that's a modern telescope. That's a stellar view, about 5 inches. Those are made down in Auburn, very fine telescopes that you can buy today. All right, let's talk a bit more about reflectors. And the most common type that you'll hear about are called Newtonians, like the example here. As I mentioned, there is the glass there, or sorry, the mirror there in the back that does the magnification. There's also that flat piece of glass that does no magnification, but gets things out to where you can see them. Reflectors can also be small or big. Examples here, the one in the top left is actually one of the library telescopes. That's the one that Bill donated. You can check that out from the library here. And that one is about 4.5 inches. When I say 4.5 inches, I'm referring to the aperture there of the telescope, or the size of the mirror diameter. The one on the bottom left is one of those that I mentioned you could borrow. That one's actually available right now from the club. That's an 8-inch telescope. I'm there next to my 18-inch telescope, and up at the top is the largest single mirror telescope in the Canary Islands. That one has 34 feet in diameter, so it's crazy big, crazy big. All right, I mentioned cat-eye-optic telescopes. I mentioned these partly because you see these a lot. These are those orange, typically orange or orange celestron, or the blue mead Schmidt-Cassegrains that you see out there. They have combinations of things that have pluses and minuses, but basically whether they're the Schmidt-Cassegrain or a very similar telescope, the Maxitop-Cassegrain, they have a combination of a lens in front that does some bending of the light. They have a mirror in the back that does a lot of the bending of the light, and then another spot on the front glass that is a mirror, and then that gets reflected back out through the eyepiece. So those combination of things all work together to give you what has an effective focal length of something that's much bigger. And I'll talk about what focal length means here in just a second. So each design has pros and cons. Refractors can make quite gorgeous images. If you ever look through Nathan's telescope, you've seen some of those things. Actually, the picture that Greg showed of the comet, that was done through a refractor. They can be quite nice telescopes. Now, however, I mentioned all those challenges with getting all the colors to line up right. There's some cost that comes about to correct that chromatic aberration. Also, with all those lenses in there, for the size of the aperture you're getting, for the diameter, they can be quite heavy. So you can look at reflectors. These have good images, maybe in some opinions not quite as beautiful as in those refractors. But because of the mirrors, you're just reflecting off of the surface, there's no chromatic aberration that you have to deal with. And because these are somewhat simpler, you can make something much more cheaply, and it's relatively easy to make a bigger telescope. And for example, Bill has made telescopes here himself that are reflectors. I already mentioned that the cat-eye-optic telescopes are a mix of both, and they have the mix of some of those pluses and minuses. But the big benefit that you get from those is that the trade-off of size and focal length is a nice balance, if that's what you're interested in. Okay, I mentioned I was going to talk about these concepts, so here we are. So focal length, that is what you see here in yellow. That's the distance from that front element to where the image is focused to a point. So it's that whole yellow part here, reflecting off of that flat back mirror. It's that total length that you see there. The aperture is the diameter of that biggest opening. So those are the two main terms that you're going to hear about when we talk about types of telescopes. There's one more that you'll hear sometimes, and that is just a combination of these two. Focal ratio is the focal length of the telescope divided by the aperture. I put up there some simple math. I mentioned that common 8-inch Schmidt-Cassegrain telescope. It is got that 203 millimeters and 232 millimeter focal length, so it's f10. Pretty straightforward math. you can have one aperture, and you can have that aperture be different focal lengths and different types of telescopes. So for example, I've shown two telescopes here. They're both 8 inches in aperture, but they have different focal lengths. One is more than 50% longer than the other one. Similarly, you can have telescopes that have the same focal length but different apertures. That small tabletop telescope that you see there has the same focal length, so essentially it is capable of the same magnification, all other things being equal, what's there, never such, as the large telescope that you see me standing next to there. But they each have their own purposes. In some cases, if you're looking at those faint objects, you're going to want that big mirror to see, to get as much light as possible. However, if you're looking at things within the solar system, if you have a big mirror, you're getting a lot of light, but you're also getting all the turbulence and all the distortion from the atmosphere in that 18 inches versus the small 5 inches that you see in the other telescope. So if you're doing solar system observing, the smaller telescope may be more appropriate. Okay, that's telescopes. I'm moving quickly through here.
Can I ask a quick question?
Yeah.
On the counted dioptrics,
Uh-huh.
is the focal length still the sum of the distance from the front mirror to eventually the eyepiece?
There's the, what you call, I guess I call it the physical focal length, and there's the effective focal length. Because there's multiple stages,
Yeah.
the actual distance is less than, essentially it's like a multiplicative effect of those multiple stages within there. So it's physically shorter. That's part of that advantage that you get by doing that. Any other questions? It's a good point to ask it before I move on to eyepieces. All right, I will talk about eyepieces then. So why eyepieces? Well, we need something to get the light focused on your eyeball. And in combination with a telescope, the eyepiece controls the magnification through that pretty basic math that you see there. Literally, it's just the ratio of the telescope focal length to the eyepiece focal length. So that almost makes it sound like you could just make one as big as possible and one as small as possible and see as much as possible, but there are limits. Useful magnification is limited to be roughly twice the aperture of the telescope in millimeters. That's a rule of thumb. When you get into different effects of diffraction and other factors. And probably most importantly, there is a limit set by the atmosphere. The turbulence, the things that are in the air, the dust and smoke limit things. Around here, a good night is probably 400x or something like that. I think I've had up to seeing things at 600x on a good night. I did hear, Lonnie's not here, but I did hear of a night up in Oregon back in the late 90s where they had perfect conditions at the Oregon Star Party, and they kept adding magnification, and they were getting up to 1500 or 2000x. And they said lots of people have gone there year after year trying to replicate those conditions, but it's never happened.
X is magnification.
And magnification, yeah. So here's an example. Again, just a little bit of math for that same telescope that I was talking about. So if I took a standard 25 millimeter eyepiece, and that's a very common eyepiece, and I divided that into the focal length of that telescope, I would get 81x. The limit that you're going to see with the telescope that's useful is about that 400x as well when you do 2 times that aperture. All right, I'm going to take a brief detour. A lot of times you will see or get, or especially if you buy a kit of a telescope, they will come with a Barlow lens. But what's a Barlow lens? A Barlow lens is basically another lens that gets inserted basically into the, where the eyepiece would go into the telescope, it gets inserted in between. So for example, if I had a Barlow, I would stick it in there and then I would put the eyepiece into the Barlow. And that has a multiplication factor essentially on your magnification. Very typical is a 2x Barlow. And you can see this as a way to essentially double the number of eyepieces that you have. So for example here, if I use the Barlow, instead of having 81x, I'm going to get 162x. So it's essentially having both a 25 millimeter and a 12.5 millimeter eyepiece. But you can also see that if I, for example, I had another eyepiece that was 32 millimeters, I could take that same Barlow and put it into there, and essentially with 3 items, I would have effectively 4 different eyepieces. So that's the little side note there, just because Barlows are pretty common out there. But they are not required. It's just another way to consider having essentially more eyepieces.
Is there any disadvantage in the Barlow?
Sometimes, it depends on the quality, of the Barlow. That's one thing. A lot of them aren't made that well. You can also get into, if you have like a 8 millimeter eyepiece and you're zooming in, you get effectively double the magnification that you get there. You can essentially over magnify and get into those limits that I was talking about. I think sometimes you can get into focus travel and things like that can affect the use as well. But I mean, they're relatively inexpensive, and it's pretty easy to try them at low cost. And actually, I have Barlows. We have a number of them that are owned by the club. If anybody's interested in trying one, and you have a telescope but don't have a Barlow, just let me know. I'd be happy to loan you one. All right, let's talk about some more concepts related to eyepieces. So first is image quality. Just a note here about the things that affect that. You can sort of think about this as if you're looking through binoculars, you'd like to have a bright image. You want it to be sharp edge to edge, and just overall, you want the image to be very crisp. And you also want contrast. Contrast is especially important for us when we're looking at the sky. If you think about it, if you have sort of a hazy gray background and sort of a faint white thing on there, it's going to be hard to see that object against what's not a very dark background. But if that background gets thrown in to be like very black, and it allows those objects to pop out much more and be much easier to see. So that contrast can be affected by how the eyepiece is made. What's the quality of all the machining? What were the coatings that are put on the lenses? Is light getting scattered around? Outside of just the direct path that would go to your eye. So that's the quick look at those sort of higher level concepts about that. Now I'm going to talk about a few more things that get into a tiny bit of math. So barrel size, eye relief, and exit pupil. Right, not much math with barrel size. Really, there are 3 standards that are out there. 0.96 is a very small eyepiece that is really not used anymore. I think we have, actually the telescope Alan has, it has 0.96 inch eyepieces. Most are going to have these eyepieces. This is the 1 1/4" standard, very common, and you will see those used everywhere. And another standard is 2 inches, and that obviously gives you a much bigger diameter. And for certain uses, that allows you to capture more light. So if you look at the diagram here, we essentially have, if you consider this to be the focal length of the telescope, we have 2 different apertures, a smaller aperture and a large aperture. And the larger aperture is going to capture more light, but depending on the size of that eyepiece, if you had only essentially an 1 1/4" eyepiece, it would only get this much and be losing some of that light, whereas a 2-inch eyepiece would allow you to capture more of that light. So in certain conditions, essentially with larger telescopes, 8 inches and larger aperture typically, you can get more light and see some fainter things than you could if you were just using a smaller eyepiece. And I really noticed that when I was upgrading my telescope eyepieces. I was really surprised at what a difference it made when I put in those first 2-inch eyepieces. Another important concept here is eye relief, and that is how close your eye has to be to the eyepiece to get the image into focus. In general, the smaller the eyepiece focal length, we went through the math before, the greater you're going to get magnification. But typically, with the way that works is you also have to get your eye closer to that eyepiece to see things. This can be particularly important if, like me, you wear glasses. And you might not be able to get your eye close enough with glasses on to look into that eyepiece and get the image in focus. And actually, most of the time I observe, for a number of reasons, I observe without my glasses. It also affects comfort. If you've ever used a relatively inexpensive but short focal length eyepiece, sometimes you are literally, you're getting your eye right up there and you can feel your eyelashes brushing against the eyepiece, and that's not really comfortable. And also, you know, you're just trying to get it right in the right spot. It can be very difficult. But there is a big trade-off here. If you want to have that same focal length, but with a greater eye relief, that adds complexity and cost to the design, and so those eyepieces for the same focal length with greater eye relief are going to cost more. And it can be quite expensive. It can be 5 to 10 times compared to the absolute cheapest ones that are out there. Another important principle is exit pupil. That is the size of the image that's formed with the eyepiece. Again, a little bit of math. All the math here is pretty straightforward. It's all division and multiplication, so hopefully not challenging anybody too much. But exit pupil is just the telescope aperture divided by the magnification. So I'm going to stay with that same example that I had before. So consider that 8-inch SCT that I mentioned before. We still have that 2032 millimeter focal length. And we have that 25 millimeter eyepiece that's in there. If you do the math, the magnification worked out to be 81x. But then to calculate the exit pupil, I take that aperture, 203 millimeters, and divide it by that magnification, 81, and I get 2.5 millimeters. So now that image is 2.5 millimeters. So why is that important? Well, it's important because your eyes also have a pupil size. And if the exit pupil is bigger than your eye pupil, you're going to miss some of that light. So you might be throwing more light at it, but relatively speaking, if my pupil is this big and the exit pupil is that big, I'm only catching part of that light. And that's what this is showing here. So the red there is essentially the biggest image that the eye can see based on its pupil, and the green is what that larger aperture is, the light that is passing on to it. So what does this mean in practice? This means that keeping the exit pupil smaller than your eye pupil will allow you to see dimmer objects more easily. In other words, you're keeping that light concentrated into the area that's going to hit go within your eye pupil. And if you think about it too, that's another reason why we like to let our eyes adjust when we go out there, so that pupil is as wide as possible. Another implication of this is that if you zoom out with a longer focal length, if you think about this, we think about if we zoom out, then all the light's getting concentrated into a smaller area, but that's not necessarily going to make the image brighter because it's making the overall image wider. So in some cases, a shorter focal length may be better to look at objects. So another little diagram here. If I have that large aperture of the telescope there to the left, and I have that eyepiece to the right, and in this case, it's putting that image in green. So something that's this big, but my pupil of my eyeball can only see that much. But if I zoom in a bit with a shorter focal length eyepiece, so if you notice, like from, let's see if I can go backwards. Yeah, from there. So this is the focal length of the telescope, and this is the focal length of the eyepiece. I'm going to shorten that focal length. And by doing that, I get that smaller image. So I'm now essentially focusing that light on the pupil of my eyeball. There's another implication. I know we're all quite young in here. Unfortunately, for those of us who aren't that young, our eye pupil, I should have said, maximum size also decreases with age. Young eyes are very flexible, and that pupil can get very wide. Yeah, please ignore the exit right up there. That should be I, your I people. So this is a consideration when you're selecting an eyepiece for a dim object. You know, that younger person might be able to see more with that same eyepiece than you can. And it's not all is lost though. You know, your experience may vary. Some folks have bigger pupils, some folks have smaller pupils. There are other factors that play into this as well. And there's also differing opinions about, you know, what is the true effective age on things. I was paging through a number of studies and saw different things. The chart there on the left, that graph is what TeleView puts on its website. I couldn't find any data to support that. I did find a paper to support the data on the right, which has a list of numbers by age. And I like the one on the right better because it actually says all of our eye pupils are bigger as we get older. So here it says 4 millimeters at 60, and over on the right it says 5.8 millimeters at 60. I'm 60, so I'm going to go with the 5.8 until I test it and learn otherwise. Again, we can do an example here. So this is me, 60 years old. I wasn't quite 60 years old in that picture. But I'm going to use that 5.8 millimeters as the maximum exit pupil that I am capable of. Again, using that same telescope, we go through the math there. So now I've got I sort of flip some terms around and figure out, you know, what that max magnification I can get with that aperture and that exit pupil, and I come up to 35x. What does that correspond to in terms of eyepiece focal length? So if I go back and do the math, that comes out to be a 58 millimeter eyepiece. 58 millimeter, that's a pretty big eyepiece, you know, and focal lengths rarely get bigger than that. So with this telescope, it's all good. Pretty much any eyepiece that I'm going to use, I'm going to be fine. But what happens if I go pull out my big telescope? So now the aperture has gone from 457 up to 457 millimeters. I take that same exit pupil, do the math there, I get a 79x magnification. What does that correspond to? Again, go through the math and figure out that corresponds to a 24 millimeter eyepiece. Well, I mentioned before that 24-25 range, that's pretty much the most common eyepieces out there. And if I'm looking at an object, I might, instead of pulling out my 31 or 41 millimeter eyepieces, which I do have, if it's a dim object, I might want to pull back off to my 21 millimeter eyepiece and see if I can see things a little better with that. So, some considerations. This is a little advanced. That's not the first things to worry about, though. All right, any questions about that before I start talking about coordinates? Yes?
Well, there's also cataract surgery.
Cataract surgery,
That helps us
too.
old folk.
Yes.
I don't know.
You know, yeah, we could talk about a lot of things. And, I think some folks, Alan, where's Alan?
Okay.
Oh, over there. I mean, you just had cataract surgery. I mean, and you had dramatic, Ray's not here, but I think you had dramatic differences in what you could see afterwards.
Oh,
Right?
yeah.
Yeah, and Corinne's saying the
Whites
same.
are white.
Yeah. I know Ray was quite happy after his too. Yeah, so if you have cataracts in your eyes that's diffusing things, that's obviously going to hinder things as well. It never hurts to have young eyes, we'll just put it that way.
Our plastic ones.
Yeah. Any other questions or comments? All right, coordinate systems. So why do we use coordinate systems and why do we have two systems? So first, we need a way to tell each other where things are in the sky, regardless of where we are and what time of day it is or what day of the year it is or anything like that. If I'm here today and I'm talking to somebody who's going to be in China 2 years from now, we all need to be able to refer to the same place for an object. But that doesn't help us when we go out and try to find an object. We need to be able to see where things are right now, too. So we'll start with the simple one first. That's altitude azimuth. In the images that Greg was showing in his What's Up presentation, those were in the alt-az coordinate system, as Bob pointed out. with that. Pretty straightforward. If you look at altitude, the horizon is 0, the zenith, straight overhead is 90 degrees, and the azimuth coordinate is just the compass coordinate. So north is 0 degrees, east is 90 degrees, etc. So pretty straightforward. The other system that we use is the equatorial system. This is a universal reference. The other one was relative to you at a particular date and time. Equatorial is universal, that we can use regardless of date or time. It is centered at the Earth's center, and it's essentially projecting things out into the sky. So things are fixed relative to the celestial poles, and it also looks at, when we're looking at essentially the equatorial horizon, so to speak, we are looking at where the equinox crosses the equator at a certain date and time. So typically that is used to be 2000 for the March equinox there, but you can also see other references too. When we look at math, the alt-az was all in degrees. Typically we use the declination in degrees here, but the right ascension, we translate that 360 degrees to hours instead, to 24 hours. But it's pretty straightforward calculation there too. So this is what you'll see in star atlases and elsewhere. One thing that is a little counterintuitive at first is that east and west on a star chart are opposite of what they are on a map. There's sort of an easy way to try this. If we were to assume, let's assume now that north is that way, towards the screen. If that's north, then east is over here. Now I want to look up at the sky, and so I want to flip my map over while keeping east. Let's see if I can do this without hurting my arm. So I'm going to point at the sky, but keep this arm pointing at east. And like that, you basically see you get twisted around. I'm not doing that very well. But basically try it yourself. You can even do it by writing on a piece of paper, holding things up to the sky, and you'll see that things get flipped. All right, example of the coordinate system. This is Albireo, and if you go and look it up in any table, well, let's look at Albireo A, the primary component of that, you'll see this position for it in those in those equatorial coordinates, 19 hours and 30 minutes, and almost 27 degrees, 58 minutes. I can go look it up on a star chart. So I've just copied the same numbers over here onto here. But if you look on the chart, you can see, look at that, come over here, 19 hours, 30 minutes, and 30, 29, 28 degrees. So that's the same. If we want to see where things are at a particular date and time, we can use like Greg was using. He was using Stellarium. That, you type in the date, put in your location, type in the time, and you can see things. So let's zoom in here a minute. So look, right there, we also see that 19 hours, 30 minutes, and that 27 degrees, almost 58 minutes. But now, for this date and this time here, and location is not on the screen, but I put it in there. I just done it for my home in Nevada City on those dates. You can see the azimuth and altitude as well. So if I were to go out at that date and time and look up into the sky, I would go to the azimuth is 86 degrees, so that's almost straight overhead. I'm sorry, the altitude is 43 degrees, so that's about halfway up. And the azimuth is 86 degrees, so that means almost due east. So that tells me how I can go find things, and it's an easy way to actually use that coordinate system. Any questions on that? I know I went through that sort of quickly, but does that make sense? Essentially, you have two different coordinate systems that are each helping you do different things.
So the alt-az is like what I've been using for Stellarium.
Yep.
That's for if you're standing somewhere and a particular star is in a particular place, it's just the one coordinate is the altitude, is the angle,
Yeah.
is the elevation above
Yeah.
the equator, of the ground,
Yeah,
right?
the ground, where your horizon.
Right, and the other one is 0 to 360, depending on what's north, south, east,
Correct.
west.
Correct.
So the Earth is spinning around, right? And that Altaz measurement will be different, right?
That's why you need to know the date and time.
Right.
Yeah.
So on the equatorial, well, right, in order to know where it is. But you're saying the equatorial system, that is the same, because that's just relating to the stars,
Correct.
right?
Correct. And we pick arbitrary zeros essentially for it. Right?
And the arbitrary 0 is where the vernal equinox is.
Correct. Correct.
And
In
then-
that one date.
Right, the one date, so that's, well, is it the same, it's a precession of the Earth affect that?
Yeah, remember, everything's moving, right?
Right.
Yeah, so yes, it does. And you'll see, and you can even see, if you go
So,
into-
so those values will be different.
those values are different. So I mentioned that there was it's J2000, right? And that means for the year 2000 essentially. But a lot of times you can go in, if you go into software, a lot of times you can type in J now, which means, essentially, what it is now. Or you can also, like, they didn't use 2000 back in the 1800s or whatever, right? They used J, 1900 or something like that, or 1950. So there were different
So the
systems.
right one is right ascension.
Right ascension, yeah.
And what's the other coordinate for the equatorial system? Right ascension?
Declination.
And
Declination.
declination is kind
Right,
of
up
how
and
high
down.
it is
Yeah,
in the sphere.
correct.
And those will change gradually with precession of the Earth.
Yeah, so if you go into the software, some of the softwares will allow you to change that, and you can like have it do that translation for you. You can see how much it changes.
But if you're talking about satellite warfare, that's probably important.
Yeah, or even if you think about, think about how high precision, the things that astronomy is doing these days. Very important. And also, we won't even get into this, right? These things assume that the planets aren't moving, but when you get into that high precision, not planets, stars aren't moving, but stars that are close to us, they do have relative motion in the sky, and part of that is measured by astronomers as well. Good questions. Any other questions or good comments? Bill? Oh, sorry, I can't see you, Bill.
You want to mention the difference in our regular daily time and celestial time? Well, we measure our daily time based on where the sun is.
Right.
But celestial time is based on a star.
Yeah.
So that's the difference, about 4 minutes a day.
Yeah.
Right, there's like a difference of, because the Earth goes around the sun,
Correct.
where our time is relative to the sun. But you have to add a day
Correct.
if you're talking about celestial time, right? I think, or subtract it. I don't know.
That's
Somehow,
I
there's a
can't get it
difference.
straight either.
There's
That's
a
why the
difference.
seasons move
Right.
in the sky, that's why it happens.
That's another good point. There's a lot of detail. I tried to keep things relatively simple, but Bill's right. There's a lot more detail we could go into here too. Any other questions or comments? All right.
You're talking about the connection between different mounts with that?
It's going to come up. That's
All right,
coming.
okay.
Coming very soon, actually. Actually, the next slide, I think. But first, some handy references, pardon the pun. If you want to get a rough idea of how big things are out there, here's a few things. Your fist is roughly 10 degrees. A finger is roughly 2 degrees if you hold it at arm's length. Your entire breadth of your hand is roughly 15 degrees. And the Big Dipper has some good references built into it as well.
So the moon and the sun are at half a degree.
Yeah, I think that was
That-
another one too. Go back.
Okay.
Yeah, width of the full moon is half a degree right there. Yep.
There it is.
Okay. As Greg was mentioning, these things relate to mounts as well. So here people talk about alt-as mounts here, or Dobsonians. These are essentially, well, this is essentially on an alt-az mount, so essentially, actually I'm not gonna get into that because that's a little more, there's not two separate clear axes on that one. That probably wasn't the one I should have brought in. If you see here in the diagram on the left, you've got one axis, the azimuth axis, that is pointing essentially straight out of the ground, and you have that altitude axis. That pivot is essentially parallel to the ground. So everything is relative to the ground where you're standing right now. With an equatorial mount, you're aligning to that equatorial coordinate system. You're going to take that mount and orient it so that one axis is pointing towards the north celestial pole, if you're in the northern hemisphere. If you're in the southern hemisphere, you pointed at the southern celestial pole. And the other axis is going to be parallel to that. So I think you can see here that it's that one that's pointing towards the pole, and this axis is perpendicular to that, and that allows you to do that inclination, or that declination, I should say. So there are trade-offs with different kinds of mounts. First, let's talk about alt-az. These are simpler and lighter than equatorial mounts. There's no alignment required if you're star hopping. So if you think about it, right, you're just set on the ground. All you're doing is making it level, and then you are moving around to go towards your object. However, if you want to track things, it gets more complex. If you think about it, as things move across the sky, you're going to be, essentially moving up and down and left and right at the same time. That makes things a little more difficult, and also when you're moving, you're essentially, if you think about an object as sort of going overhead like this, but your telescope is essentially staying with its one axis pointed parallel to the ground, so you get that field rotation that you see there. I don't know if that's coming out very well. I don't think it is. What this is showing is, better on my screen, that you can see there's a picture frame that is staying essentially a square around here, but the object is rotating relative to that picture frame. I can show that later. So if you're doing astrophotography and you're trying to do long exposures, you're going to see movement in there as you track. With the equatorial mounts, these are more complex, and these are heavier than, sorry, I got the wrong words in there, than the alt-az mount. You have to do that alignment that I mentioned before. If you want to have that axis, point to the celestial pole, point to the North Star, you need to do an alignment. You need to figure out exactly where that is. But once you do that, things are simpler. You only need that one motor if you think to track. So if you think about it, with the telescope here, if this axis is pointing at the celestial pole, everything is rotating around that. So all you have to do is rotate that motor to track something as it goes across the sky. Just track that in time with the star's movement. It's not showing out here again, but in this case, because you are essentially following that same movement across the sky, the frame of the picture is going to rotate around as well. So that's better for photography. So if we look at alt-az mounts, they can be small or big. Again, you got the small one there on the left. That's the telescope that Bill donated, and there's the medium one. That's one that you can borrow. And on the right is, Lonnie's not here tonight, but that's Lonnie's telescope that he made himself. All of those are on alt-az mounts. Equatorial mounts can be small or big too. On the left is one of the club telescopes. I think that's the one you have, Karen, right? Quite sure, I think.
so.
And Greg is there in the middle with his. That's getting a little bigger and a little heavier. And on the right, you can see that's that big 40-inch telescope that's up in Wisconsin. And if you can see down here, There's a person standing right there, so obviously that's a very big mount. You can have the same telescope, but you can put it on different mounts. So this is one of those common 8-inch Cassegrain telescopes. On the left, that's an alt-az mount. You can see that bottom base is parallel to the ground, and the other axis is essentially perpendicular to the ground. Or sorry, that is parallel to the ground. The other axis is pointing straight out of the ground. On the right side, this is the same telescope, but it's been put on a wedge, and it can be oriented such that it is that axis there is pointing at that north celestial pole, and therefore you can have the same telescope on different mounts. And some cases, one's going to be more appropriate and easier to use, for example. But if you wanted to do a photography, you might want to set it up like that. This is the same telescope here. This is my telescope, but this is also on different mounts. So on the on the left, you can see that is flat on the ground. But on the right, actually, I bought an equatorial platform from Tom Osipowski, who's one of our club members. And that allows a certain amount of tracking. It's not going to do that full rotation like you saw on the other mounts, but you can track for a couple hours. It can rotate for about 2 hours, and then it runs out of travel and you have to reset and do things. But it gives you a tracking for a limited time. All right? Yep.
When you're trying to do photography with these telescopes, the platform allows you to photograph, whereas if you try with just a go-to sort of thing, you get field rotation and you can't use it for photography.
Exactly. It's all the same principles that I tried. Unfortunately, those pictures didn't come out well that showed that field rotation, but I can show it on the laptop or on my computer screen afterwards if anybody wants to see it. But it's just what Bill said.
Question.
Yeah.
Because I understand how the equatorial mount works, because it's just rotating around that axis that goes through Polaris, right?
Yeah.
And just keeps on going this way, and then
Yeah.
maybe the mount has to be adjusted, as you're saying. How does the alt-az know how much each motor, because depending what you're looking at, the motors are gonna move at a different speed depending on how high it is. So how does it,
The alt-az is computerized.
So it knows what angle it's at?
You have to do an alignment. You have to tell it exactly where it's pointing, so it knows where it's starting, and it knows where it's oriented the whole time, and it's doing the math.
Oh, well, so if it knows it's pointing at a certain place.
And it knows where it knows where it is, and what the day and date is, all that sort of thing.
And then it knows how much to move in this axis and how much
Correct.
to move in the other axis.
Correct.
To a certain degree.
Yep.
But then it rotates this.
So yeah, so it's got
Those
to
two
move
dots
out.
will move a little too much.
Each motor is going to move the right amount.
Okay.
But that's why the other one is easier, because it's just one motor and it's moving at a constant rate, just the rate of the rotation of the sky. And in this example, it's simple too, because once you align it, there's not you can't see the axis because it's essentially swinging that whole thing through an arc. It's a virtual axis, but it's doing the same thing. And it's just one motor that's run off of a 9-volt battery, no computer required.
I mentioned something else.
Yeah, go
You have a
ahead.
star party and you have a big telescope and it doesn't have all that sophistication. What happens? Every couple of minutes you gotta run up the ladder and move the telescope.
Exactly.
And you always try to get some kid to do the same thing for you.
Well, they have a couple of minutes to do that. You have to change every couple of minutes.
And if you notice that normally I bring my smaller telescope with the computerized mount to star parties, because it tracks, well, there's a number of advantages. One, it's not as tall, so shorter people can see into it, but the computer does all the tracking and I don't have to do things. At least that's what I did before I got the equatorial platform. All right, here's a pop quiz. What is this telescope? Is it alt-az or equatorial?
Alt-az.
Alt-az. Very good.
How can you tell?
Good question. Well, look at the axes, right? So you got one axis that's parallel to the ground. See this bar? That's the axis, so it's pivoting over there.
Oh, I didn't see the bar, okay.
Yeah.
And the other one is just the vertical.
And the one is just vertical.
It's a post.
Yeah, exactly. Thought I could fool folks, but no. So, actually, we just touched on this a little bit, with the comments that we just had. So, this is alt as. So, I showed that that picture of the telescope that Karen has, the club loaner that she has. We could buy a simple, cheap motor. I think they're like $25 or something, that attaches to that, and that will, once you do the alignment, it will track that telescope across the sky. You can spend more money than that. This is a very nice, expensive mount. Actually, this is similar to one that was donated to the club. That was the way. It's like the one you had for a while. I think you and
Never took it out.
yeah, you never took it out, and I think you and Paul got it out once and set it up. I
Right,
remember.
Ray, Paul showed Ray and I had it.
Oh, Paul showed
I never
you.
took it out.
Yeah, yeah. I mean, but it's a great mount. It can do a lot of things. It's used for a lot of photography.
80 pounds.
Yeah, it was heavy. It was heavy.
But I
But
say that motor mount, that motor drive.
it's got a motor. It actually has two motors, so it can do go-tos as well. So it only needs one to track. But if you want to, type into the computer controller there, go to this object, you can do that with it too.
So the one that's tracking is essentially a 24-hour clock.
That it's essentially rotating on that 24-hour. Well, actually, the celestial period that we were talking about before.
Going opposite the way the Earth is turning.
It's yes, because it's tracking. It's watching the sky.
Rod?
Yeah.
Funny that Alan should mention clock, because in the old days, 60s and 70s, they used to call them clock drivers.
Oh, that's right.
Remember those days?
Yeah, that is right. So up in the upper right is that's essentially the same telescope that I have, my smaller one that you saw before. Actually, the club has one of those as well. The Furbies have one of them now, and because of that computer system, it's computers that have made these sorts of go-to mounts what they are and relatively inexpensive. That hand controller, so you can see, this is an alt-as mount. So it has to do that complex movement, but it's a relatively speaking inexpensive computer that can do that and do all the math these days. Let's talk a little bit about navigation aids, and there's a variety of these too. First is to talk about its finders. Every scope is going to have a finder, and that's because if you look just through the eyepiece, you're only going to see a small amount of the sky, right? To figure out where you are and where things are, you need to be able to see a bigger amount of the sky, and that's what the finder does for you. There are a number of different types. One of them you'll see on a lot of the telescopes that we have in the club are reflex finders. Those are your telrads. I have a picture of one coming up. A quick finder is a very similar thing. They project essentially a bullseye up onto the sky. You can also have a red dot finder. It's a similar thing. It's just projecting literally that, a red dot up in the sky. You can have a finder scope. Literally, that's just sort of a wide-angle telescope that's mounted in parallel to the main tube of your telescope. Or you can have green lasers. There's a green laser on that red telescope up there right now. Each of these have trade-offs. Some are easier to use than others. Green lasers have their own downside. Great if you're out there, by yourself or with a group where everybody's looking at the same thing. But if someone's out there trying to do astrophotography, you're going to mess up their pictures. So you'll find that a lot of star parties, bigger star parties, they're prohibited. Here's that virtual view you see up there on the right. You see that bullseye projected there and the stars through there. And you can use these in parallel, like the example there on the upper left has both a finder scope and a telrad finder. There's the green laser. If you haven't seen one of those, I can't remember if there was one out. Yeah, oh,
Alan-
had a green laser.
Alan
Yeah,
uses
yeah,
it a lot.
yeah, he had a green laser, that's right. It's great, because you can point it straight up at the sky and see exactly what you're looking at. Everybody can see it at the same time. It's great for outreach. Another navigation aid is setting circles. These are literally marks that are on the axes of the telescope. And once you get aligned, you can set those zeros in the right location essentially, and those will help you navigate to those coordinates that you saw in those screens that we had before. However, just the manual ones aren't super precise. You're looking at a small angle sky. We're looking at fractions of a degree there. If you can see there in that picture, the smallest gradations on there are 2 degrees. So,
Right.
yeah,
Pre-computer, not so long ago in our past,
yeah.
like in the 70s, this was the way you did it.
It was the way you did it for sure. You did that, and you got zoomed in, and
Yeah,
then you
then you
used,
get a little close, and then you,
used your finder to zoom in more, and you'd star hop around and things like that.
Yeah.
Match the star pattern. Exactly right. And a lot of people still do that, right? And I'm going to get talking about a little bit about some of the advantages and disadvantages of these different methods, but a little preview is that if you're doing that, you're going to learn the sky. You're going to get out there and you're going to see the whole sky out and learn where things are. But we have a few more advanced things now that we can use. One is, essentially those electronics. You can have encoders. Essentially, these are devices that are measuring the rotation of each axis, and you can feed that into a computer, and when you do that initial alignment of the computer, then it knows where things are, just like we were talking about before. Another thing that's come out in the last 2 years is what's called plate solving. It used to be, folks had cameras and they had laptops that would do it when they're doing astrophotography. Now you can get standalone units that do plate solving. What plate solving is a camera. It's looking up the sky and it's seeing the star patterns that are in there and it's saying, okay, based on those star patterns, I know where I'm pointing. So you can have, and I have one of those on the left, and Paul bought one recently too. On the back of this, you can see down here is a little camera. It just sits there and reads the sky, and it feeds back to my iPad and tells me where I'm looking. And based on that, it can also, if I tell it where I want to go, it will help me navigate to that. So it's a little self-contained device there. So that's one example. This is another similar example on the right. This is one. It's just a standalone camera, and you connect it to your tablet or phone via Bluetooth or Wi-Fi, and it does all the same thing with that. So there are trade-offs here. The simpler aids, like I mentioned, pretty straightforward. There isn't stuff to break. It's hard to break setting circles unless you physically peel them off your telescope. You can run the batteries out on your reflex finders, but it's pretty easy to carry a spare set and change those out when they get low. And as I mentioned before, when I was talking there with Mark, it's a good way to learn the sky. And you do need a little skill to star hop to faint objects, but it really helps you develop that skill. And there's a lot to be said for getting out and doing that. If you get into those computerized aids, it's easier to find faint objects. If you're looking at some little planetary nebula that hard to distinguish from a star, a lot of times it's very helpful to have the computer point you exactly where it's at, and then you're still hunting around a little bit, but at least you know you're in the right vicinity. If you're using a plate solver, the alignment is super easy on those too. Basically, you point in one area of the sky at a bright star. The screen comes up and says, "Okay, tell me, see these stars. Tell me which one I'm pointing at," and you select it on the screen, and you're aligned. Other ones, like with those encoders they saw, usually you need 3 stars, sometimes 2 depending on the computer, to do the alignment, but 3 is what's typically used to give you an accurate alignment. So you have to point it at one star and get it all centered and everything and hit enter, and then you go over and another part of the sky and point another one, get everything set up and enter that and do that a third time. So it takes a little bit of skill there and some patience there to do that. It's also important to know though that don't expect everything to be push button. You get these computerized systems out there and we think, oh, it's going to be great, all I have to do is go out and do it. Things never work that easy. There's always going to be something that you have to figure out and get working. So it does take some basic knowledge of the sky to get out there and use those things correctly. And when they don't work, it can be super frustrating. It can be super frustrating. I think anyone who has a computerized telescope system has had that experience. So, trade-offs. Everything's got its pluses and minuses. All right. Any questions before I start talking about now, with all that knowledge, what you should get? No? All right. So, I sort of gave away the answer here, but I think if you saw my presentation back in May, you probably anticipated this. What telescope should you get? You should get one that you're going to use. You want something that is simple enough and light enough that you'll take it out and use it and appropriate for your skill level. And maybe for you, the answer is none. And at different points in life, we have different things going on. And for me, until just a few years ago, the answer was none for me. So it was only recently that I finally got a telescope.
Or binoculars.
Yeah, or binoculars, yeah. And that's coming up here again too. If you have one that you're not using, I encourage you, there's lots of people who could use that telescope, pass it on and use the money to get something that you will use. Just as Greg was saying, and this slide was literally taken from my last presentation, you can get out there and enjoy the sky with whatever you got. You've always got your eyes. Take out the planisphere with you, and then you've got your navigation aid too. Binoculars are great. As I mentioned, I always take out my binoculars. Small telescopes. If you're going to go out and spend time looking at the moon, the planets, and the brighter objects, something like this one that's on the table here, that's 5 inches. Very easy to take out and use. If you want to get something that will look at a few more things, a medium-sized telescope will do that. Gets a little more effort involved, but it gets you more magnification. And you can keep going from there, right? You can get as big as you want to go. And there are, Bill had 23 inches, Bill? 22? 22, yeah. There are people in the Bay Area with 28 inches. What guy in Texas has, what's Jimmy Lowry's, like 48 inches or something like that? Something huge.
You're obviously talking about reflectors.
Yeah, reflectors. These are all reflectors. These are all reflectors, yeah. You can get very big, and you can see fainter and fainter things. But, keep in mind, you can see fainter things, but they're not necessarily going to be bigger, which is fine. And of course, the bigger and heavier are, the harder they're going to be used, and the less likely it is that you will take it out and use it. And a telescope is useless if you don't use it. Okay, so you've gone through all that, you say, yes, I really want a telescope. What should you consider? First, think about, are you happy with what you have now? Are you satisfied with what you're seeing now, or do you want to see more? Then think about, all right, am I going to see more? What is it I want to look at? Am I going to look at the moon and planets? Or am I going to look at dimmer objects? All these targets are completely fun and great things to look at. It's just really, what do you want to do? Then we get into thinking about how do I direct that telescope? Do I want to really sort of become knowledgeable about the sky and be able to look up and see where things are, right? Or do I want to dig for fainter objects, right? If I want to get that knowledge of the sky, I'm probably going to stick with more of those manual methods. I find myself, I spend a lot of time using my computerized telescope, but I'm finding myself going back to more of the manual stuff because I feel like I haven't really developed that knowledge and that feeling for the sky, and I want to do that. So I'm finding myself spending more time there these days. Where will I use the telescope? If you're only going to use the telescope at home, and you got a place to set it up and make it relatively accessible, so you just wheel it out maybe you can have something a little bigger if you live in a dark spot. You're happy to observe at home. But if you have to tear that down and take it apart and move it back and forth, to go out somewhere to see, that's going to be more challenges. So you might want to consider something different there. Relates directly to the next thing, how light and simple versus heavy and complex. What's my personal comfort level with that? How good am I with computerized things? How patient am I? Do I enjoy getting in there in debugging processes? Or do I think that's all a waste of my time and I don't want to do that? And then of course it's money, right? You can add on as many dollar signs as you want to add on.
Rod, I think you missed maybe one.
Oh, what's that?
Will it fit in the car?
Will it fit in the car? Very good point. It's a very legitimate point because that big telescope, literally, I measured my Prius, and that limited what telescopes that I would buy. Very good point, Mark. With any telescope, one thing I want to point out here, don't skimp on the mount. You could have a great telescope on a poor mount, and the poor mount's going to make a great telescope, a poor telescope. You can really, if you're sitting there and the thing is taking forever to settle down, and anytime you touch it, it sits there and vibrates for a while. Don't do that. It's a waste of time. And keep in mind too that you'll read that this mount is rated for 80 pounds or something. You're like, not really. Always take those numbers and 2/3 or maybe half at the most of what they specify. You'll be much happier and things will work much better that way. Okay, all that. So you're still ready. I'm still putting you off a little bit longer. So what should you do? Go to a star party. See the different types of mounts. I think folks were at the star party at Anya's, right? I think everybody was pretty friendly, right? You could talk, you could see what other people have, you can take looks through their telescopes. It's a great way to see what's out there.
There's a variety of different types of telescopes.
There's a variety of different types, exactly.
Over there.
Yep. That's why one of many reasons why star parties are great. You can borrow a telescope for free, right? It's like, hey, what's cheaper than free? I guess I can pay you to take the telescope. But I'm not going to do that, but I will let you borrow a telescope a year for free. As a member, you are entitled to do that. As I mentioned, we got some available. It's a very easy way to test the waters. You can have the telescope for a year, and then you can give it back, or you can say, hey, I think I'm ready to get one myself. All right, all that, got it. Consider buying used. Almost all the equipment that I bought used, and you can save a ton of money. You can save a ton of money that way. There's all sorts of places out there, the normal Craigslist and Facebook, but also there is a very active online forums with classified ads called Cloudy Nights. A lot of great discussions in there. I've bought and sold a lot of stuff on there. Okay, to wrap it up here, I'm going to come back to Brown's first law of observing. I had that in my presentation in May. The key here that I want to bring up is sometimes I have to be reminded of that for myself too. Greg and I were talking a few days ago, and he called me relatively early and said, "Oh, it's just too early." I said, I always wake up at early, like 4 a.m. He's like, 4 a.m. Do you go out and observe? It's like, well, not really. You have to go out and drag the stuff out. It's such a hassle. It's like, wait a minute. He was like, come on, you got to go out. And I had to step back and look at what are all these things I've been talking about? Well, apply them to myself. Because I've been thinking about taking my big telescope, I have to pack it in the car, and then I got to go out to Washington Road, blah, 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 all that effort, right? And I wake up in the morning, I do one of that. So it's like, Greg's right. So I took that telescope the night before, I set it out, and I set my tripod out with it, and I had my clothes out, and my red light right before I went to bed. I got up, woke up at my normal 4 in the morning, put on the warm clothes, put on the red headlamp so I kept my eyes as soon as I got out of bed. Went out, in 5 minutes I was sit up and looking at the sky through that telescope, and I had a great time. I really had a fun time. So, really, it's like, get out there, whatever you have, it's gonna be fun. And I got that big telescope and I had as much fun with that little telescope that morning too. So with that, go out and observe, you know. If you have any questions about any of this stuff, feel free to follow up with me afterwards.
Did you make the mistake of keeping track of how much you've spent on your?
My wife has an astronomy category in Quicken.
Whoops.
I have not gone and looked at the totals. I keep telling her, some of those were for, purchases for the club, and I got reimbursed. She said, oh, I'm keeping track of that too. Anyway, yeah, so.
Thank you.
Thank you.
Bravo, bravo.
Any other questions?